The moon is not standing still tonight. Even now, as you breathe gently in the dark, it is drifting away, slowly, silently, at a pace so small it feels impossible. Just 3.8 centimeters each year, a motion first measured by the laser reflectors left during the Apollo missions. Yet this quiet retreat has been going on for billions of years, a consequence of tides, friction, and the long gravitational conversation between Earth and its oldest companion. It's a reminder that even the most familiar things in our sky are changing, reshaping the future in increments too soft for human senses to notice. And if this quiet journey brings you a moment of rest or wonder, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep this calm corner of the universe glowing. Thank you truly for being part of it. Now, we drift into the first part of our story. Part 1. Why is the moon leaving us at all? The moon's retreat is not a mystery of emotion, but of motion. Every wave on Earth, every shifting tide, every slow tug of water against the continents transfers energy from our spinning planet to the moon's orbit. Over millions of years, this exchange pushes the moon outward, one quiet centimeter at a time, a drift written into the equations of tidal friction and confirmed through decades of laser measurements from the Apollo reflectors. It is a separation so slow you would never feel it, yet constant enough to reshape Earth's future. To understand this quiet drift, you first need to picture the Earth, not as the steady ground beneath your feet, but as a world in motion. Our planet spins once every 24 hours, turning so consistently that the sun appears to rise and set with perfect reliability. But this rotation isn't free. Every movement of water across Earth's surface, every tide pulled by the moon's gravity, exerts a subtle drag on the planet. It slows Earth down, almost imperceptibly, but always. The slowing of a day by milliseconds every century is not a poetic exaggeration. It is written directly in geological records, fossil corals, and sediment layers that preserve the rhythm of ancient tides. NASA describes this process simply. Tidal friction is one of the universe's slowest engines, but slow does not mean weak. Across millions of years, this gentle engine has been powerful enough to alter both Earth's spin and the moon's orbit. Because when Earth loses rotational energy, that energy doesn't vanish. It is transferred outward, increasing the moon's orbital momentum and gently expanding its path around us. You can imagine the Earth-Moon system like a pair of dancers connected by an invisible gravitational thread. Earth spins rapidly, the moon circles slowly. As tides drag against Earth's rotation, the thread tugs outward, and the moon drifts away, centimeter by centimeter, year after year. This is not theory. It is something scientists can measure with extraordinary precision. During the Apollo missions, astronauts placed small arrays of corner cube mirrors on the lunar surface. Even now, scientists fire laser pulses from observatories on Earth, watch them bounce off those mirrors, and return 2.5 seconds later. By timing that round trip, they know the moon's distance to within millimeters, and those measurements show the same result decade after decade. The moon is slowly leaving us. To understand why, you have to picture the shape of an ocean tide, not simply water rising and falling, but water being pulled ahead of the moon's orbit. Because Earth spins faster than the moon moves around it, the tidal bulges created by the moon's gravity don't sit directly beneath the moon. They're carried slightly ahead by Earth's rotation. And this misalignment is everything. It turns tides into a gravitational lever. These forward-leaning bulges pull on the moon, giving it a tiny forward nudge. That nudge increases the moon's orbital energy and pushes it farther away. At the same time, that pull creates a backward torque on Earth, slowing its rotation. Every push the moon receives is taken from the spin of the planet beneath your feet. Energy has to go somewhere. Nature never forgets that rule. If you could speed up time, faster than centuries, faster than millions of years, you would see the Earth's days lengthen and the moon drift outward in a slow spiral. At first, the change would look like a breath expanding, subtle and almost still. But then, as thousands of years passed in mere seconds, you would see a widening arc as the moon climbed farther and farther away. This process began long ago. In Earth's early history, the moon orbited much closer, so close that it filled the sky with a disk many times larger than it appears today. The tides were enormous then, lifting oceans thousands of kilometers along Earth's coasts, reshaping shorelines, stirring heat through the ocean and the crust. This energy exchange was fierce but predictable. Just as a spinning skater slows when she extends her arms, Earth slowed as it pushed the moon outward. Today, the system is calmer, the bulges are smaller, the drag is gentler, but the mechanism is the same, operating in silence day after day. If the moon is drifting away, why can't we feel it? Because the distance grows at the speed fingernails grow. Because human lives are too short to perceive a change that takes millions of years to become visible. Even ancient civilizations, Egyptian, Mayan, Greek, lived under a moon almost identical to ours. The moon's retreat is something only science could ever reveal, because human senses exist on timescales too small to feel it. Yet the data is clear, and the consequences are real. As the moon moves outward, the length of a day stretches. In the age of the dinosaurs, a day lasted about 23 hours. Go back to the earliest animals, long before the appearance of mammals or fish, with bones, and a day was closer to 21 hours. And earlier still, when Earth was young and spinning rapidly, a day may have lasted only a few hours. The moon's drift has been transforming time itself, steadily slowing the planet's rotation into the familiar 24-hour rhythm we now live by. This soft reshaping of Earth's rotation also affects the tides. When the moon was closer, tides were violent and frequent. Today, they are gentler. Millions of years from now, they will soften even more. Coastal ecosystems, salt marshes, tidal flats, coral reefs, evolve in step with these rhythms. As the tides weaken, life will adjust again, following the moon's slow migration across the sky. But perhaps the most profound effect is on Earth's stability. The moon acts as a stabilizing weight, reducing the wobble in Earth's axial tilt. That tilt is what gives us seasons. Without the moon, Earth would wobble more chaotically and climates would swing much more drastically. The moon's outward drift will gradually weaken this stabilizing force. In the far future, Earth may wobble more freely, shifting climate patterns and altering the long cycles of ice ages and warm periods. This is the quiet irony of the moon's escape. It is moving away because of tides, yet those tides help maintain the environment that allowed life to flourish here. And the process never stops. Earth continues to slow. The moon continues to drift outward. The dance continues, even though we cannot feel it. Scientists can even predict the distant future of the Earth-Moon system. Billions of years from now, Earth will rotate so slowly that one day will equal the time it takes the moon to orbit us. At that moment, Earth will become tidally locked to the moon. One side of our world will forever face the moon. The other side will never see it again. This is the same fate that locked the moon to Earth billions of years ago. And over even longer timescales, the sun will intervene. As it enters its red giant phase, the gravitational balance of the solar system will shift dramatically. The moon's drift, so steady today, may reverse or accelerate depending on the sun's pull. The Earth-Moon relationship, so stable to us now, is only temporary. Another pattern written in cosmic time, not human time. For now, though, the moon's retreat continues quietly, precisely, always. Each year, a few more millimeters, each century, a few more centimeters, and over the span of a planet's lifetime, enough to reshape tides, alter days, and eventually change the face of Earth itself. The moon is leaving us. Slowly, gently, obedient to the laws of motion that govern every world. And as we follow this quiet drift, one question naturally rises. If the moon is moving away, what began its journey? That is where our next part begins. Part 2. The ancient dance between Earth and Moon. Long before the moon slowed into the familiar face we see today, it circled much closer. So close, it filled the sky like a world suspended above us. Back then, Earth spun faster, the tides were higher, and each day was shorter. This early dance was chaotic but precise, a gravitational conversation that has softened over billions of years into the quiet drift we measure now. The physics of this partnership is written in tidal bulges, orbital mechanics, and the long, slow loss of rotational energy. To imagine this ancient relationship, you have to picture an Earth very different from the one you know. The continents were still molten in places, the oceans freshly formed from condensed vapor, and the moon, newborn from the violent collision that likely created it, hung low and enormous in the sky. Its glow would have been brighter than any full moon you've ever seen. Its pull on the oceans would have been immense, and each night it would have swept across the heavens much faster than today, because it orbited closer and Earth rotated more quickly beneath it. In those early ages, a day may have lasted only 5 or 6 hours. The young moon circled the planet in a fraction of the time it takes today. This closeness made the tides not gentle shore-bound pulses, but massive planetary waves. Imagine oceans rising and falling not by meters, but by hundreds, powerful enough to carve coastlines, stir heat deep within the crust, and pull on the Earth with a force far greater than the quiet tug we see now. This was the beginning of the tidal dance. When the moon tugs on Earth's oceans, it raises 2 bulges of water, one facing the moon and one on the opposite side. These bulges don't sit perfectly beneath the moon. They're carried slightly ahead by Earth's fast rotation. In the moon's early days, that offset was far greater than it is today because Earth was spinning so quickly. This misalignment is what allows energy to flow between Earth and moon. The moon pulls on the bulge ahead of it, trying to drag it backward, but Earth's rotation carries the bulge forward, resisting that pull. The result is a constant tug of war between spin and orbit. Slowly, friction within Earth's oceans and crust converted rotational energy into heat. And as Earth lost some of its spin, the moon gained orbital energy, so it moved outward little by little. This is motion, written not in sudden events but in geological patience, centuries stacked upon centuries, building toward change. Even now, the planet bears the scars of that early tidal violence. Ancient rock layers shaped by enormous tides, evidence of intense gravitational heating in the moon's interior, and subtle asymmetries in the moon's crust that record its early deformation. As the moon drifted outward, the system began to settle. Earth's days lengthened, the tides softened, and the moon's orbit slowed until the two bodies reached a more harmonious state. Yet harmony did not mean stillness. The dance continued, just at a gentler pace. The moon's rotation also changed during this time. When it formed, it spun freely, perhaps completing a rotation every few hours. But Earth's gravity created a bulge in the moon as well, slightly stretching it along the direction of Earth's pull. This bulge, too, lagged behind its ideal alignment because the moon was rotating faster than it orbited. Each lag exerted a braking force on the moon's rotation, gradually slowing it until one side became locked facing Earth. That lock, so perfect and ancient, remains today. Once the moon became tidally locked, the nature of the dance shifted again. Earth continued to lose rotational energy, and the moon continued to drift outward. But now the motion settled into a quieter rhythm. The massive tidal waves of the early Earth died down. The enormous gravitational heating inside the moon cooled, and the orbit began to resemble the calm, predictable path we observe in the modern sky. If you could see this transformation sped up to the pace of a heartbeat, you would witness something astonishing. The Earth spinning like a top, gradually slowing. The moon spiraling outward in a smooth, widening arc. The tides, once towering and violent, shrinking step by step. The entire system relaxing from turbulence into long-term equilibrium. But the equilibrium was never perfect. Even after billions of years, the dance hasn't ended. Earth still slows. The moon still drifts away. The same forces that shaped the early system continue their delicate work, just with far less urgency. Today, the moon recedes by about 3.8 centimeters per year, a tiny distance over a lifetime, but monumental over the history of a planet. This retreat is not a relic of the past. It is a motion happening right now beneath your feet in every rise and fall of the sea. Yet the ancient dance has consequences that go beyond motion. Earth's axial tilt, the 23.4 degrees that give us seasons, is stabilized by the moon's presence. Without the moon, Earth's tilt could wobble wildly, swinging from nearly upright to deeply angled over long spans of time. Such variations would cause dramatic climate changes far exceeding the patterns we know. The moon's mass, distance, and gravitational grip serve as a cosmic anchor, calming the tilt and creating the environmental stability life depends on. As the moon moves away, this stabilizing influence will gradually weaken. The wobble may grow, climate patterns may shift. The seasons could change in ways that seem subtle over human time, yet profound over geological eras. This, too, is part of the ancient dance, a ripple of change that echoes across the ages. The relationship between Earth and Moon is also encoded in the length of the month. When the Moon was closer, it orbited faster, completing a circuit in just a few days. As it drifts outward, its orbital period increases. The modern month, a lunar cycle of about 27.3 days, is a product of that long drift. In Atia, the far future, a month will grow even longer as the Moon's orbit continues to expand. Every part of this partnership, days, months, tides, seasons, is shaped by gravitational exchange, a world and its moon moving together, changing together, influencing each other across billions of years. It is humbling to think that our familiar sky, the one humanity has poemized and navigated by for tens of thousands of years, once looked entirely different. The early moon was brighter, larger, more powerful. Its influence on Earth was immense, and its slow retreat is what allowed Earth's rotation to calm into the steady rhythm we experience now. The ancient dance is still underway. We just live in a moment where the steps are too slow to see. But the physics that set this relationship in motion continue to guide it, just as reliably, just as quietly, just as inevitably as they did 4 billion years ago. And this soft departure brings with it a deeper question, one that reaches farther back into time. What was the moon like when it first formed, and how did its earliest closeness shape the fate of our planet? That is where our next chapter begins. Part 3. When the moon was once much closer. If you could stand on ancient Earth, you would see the moon looming enormous above the horizon, 3 to 10 times larger than it appears today. Its pull would reshape oceans, shake the crust, and lift tides hundreds of times higher than the ones we know. This early closeness explains why the outward drift began at all. As Earth slowed, the moon's orbit expanded in perfect response, conserving angular momentum in the way all celestial systems must. To imagine this world is to step into a time when Earth was young, molten in places, wrapped in steam and ash, and only beginning to form the landscapes we now recognize. The moon was newly born from the aftermath of a colossal collision, likely between the early Earth and a Mars-sized body. The debris from that impact gathered, fused, and cooled in orbit, forming the moon in a matter of weeks or months. But its first orbit was nothing like the graceful path it follows today. The newborn moon circled Earth incredibly close, perhaps only 20,000 to 30,000 kilometers away, far less than its current average of 384,000 kilometers. At that distance, it dominated the sky. Its presence wasn't the gentle glow we know now, but a brilliant, oversized world casting stark shadows across the ground, rising and setting at a dizzying pace. And every one of its movements tugged fiercely at Earth's oceans. Those early tides were not subtle. Imagine entire coastlines swelling and retreating with unimaginable force, the ocean rising hundreds of meters and then falling away again. These tides were like great planetary breaths, slow, deep, and unstoppable. They stirred heat through Earth's oceans, fractured young crust, and sent powerful currents racing across the newborn seas. But the tides did more than shape the surface. They were the beginning of a long gravitational exchange that would connect Earth and Moon forever. As the moon pulled on the oceans, Earth's rapid rotation carried the tidal bulges ahead of the moon's orbit. This offset created a gravitational lever that changed everything. The bulges pulled forward on the moon, giving it extra orbital energy. Earth, in turn, was forced to slow ever so slightly to compensate. Even in those early days, the laws of angular momentum held firm. If Earth loses rotation, the moon must gain orbital distance. It is in this exchange that the story of the moon's retreat begins. The moon's closeness also shaped the nature of Earth's nights. Even without city lights, the darkness would never have been absolute. Moonlight would have been so bright that shadows stretched sharply across the landscape. Nocturnal life, had it existed then, would have lived under a sky far brighter than any modern full moon can produce. And because the newborn moon orbited so quickly, perhaps circling the Earth in only a few days, it would slip across the sky with a sense of urgency we no longer experience. Its phases changed more rapidly. Its path shifted more dramatically. Its gravitational influence was relentless. Over time, this intense gravitational interaction produced effects deep inside Earth. Friction stirred the mantle, altered convection patterns, and contributed heat to the young crust. The tides, in their own way, were helping to shape the early stability of Earth's geology, redistributing energy from the violent birth of the planet. Meanwhile, the moon was undergoing its own transformation. It too experienced tidal flexing, its interior squeezed and stretched as Earth's gravity played across its surface. This generated heat inside the moon, keeping parts of its interior molten for far longer than they would have been otherwise. The vast, dark plains we now call mare, the lunar seas, are evidence of these ancient flows. They formed from volcanic eruptions, many of which were powered by the tidal heating that occurred when the moon was closer. In this sense, the moon's early closeness sculpted both worlds. Day by day, the Earth-Moon system continued its exchange. Earth rotated rapidly, losing a little angular momentum with each passing tide. The moon absorbed that momentum, climbing outward in its orbit. It was a slow spiral, a quiet motion measured not in days or years, but in millions of years. And as the moon drifted farther away, the violence of the tides began to soften. A day that once lasted mere hours grew longer. Tides that once shook the crust began to settle into the familiar ebb and flow we know. The moon's orbit slowed as its distance increased. The once fiery, molten lunar interior began to cool, and Earth gradually began to stabilize. This shift from closeness to distance, from chaos to calm, is one of the most important transitions in Earth's history. Because if the moon had remained too close for too long, its immense tides might have prevented the formation of stable coastlines and continents. Its gravitational pull might have stirred Earth's mantle too violently. Climate cycles might never have settled into a pattern long enough to support life. The moon's retreat brought balance. It allowed the Earth-Moon system to relax into the harmony we live with now. But even as the system settled, the moon's early imprint remained. The tilt of Earth's axis, the angle responsible for our seasons, was influenced and stabilized by the moon's initial closeness. Without that early gravitational weight, Earth might have tilted wildly, like Mars, whose axial tilt swings dramatically over long timescales. Such wobbling could have created extreme climate cycles, making long-term habitability far more difficult. Instead, the moon's early presence smoothed Earth's rotation, creating the foundation for stable climate patterns. Oceans could form and remain. Weather systems could establish themselves. Life, eventually, could begin its long, slow rise. The moon's closeness also shaped the length of the month itself. In its early orbit, the moon completed its cycle quickly. But as it drifted outward, its orbital period lengthened. The modern lunar month, 27.3 days, is a product of billions of years of gravitational negotiation. Every phase of the moon, every orbit, every eclipse still carries the imprint of that early spiral outward. If you stood on the ancient Earth and watched the moon rise, it would have filled a massive portion of the sky. But from the moon, the sight would have been even more spectacular. Earth would have hovered huge and bright in the lunar sky, rotating rapidly beneath swirling storms and glowing volcanic plains. One hemisphere of the moon would always face this world, its surface lit in shifting blues, greens, and whites. The other hemisphere would never see Earth at all. This strange duality, one face forever watching, the other blind to its parent world, was established early, during the moon's closest approach. Tidal locking occurred long before the moon reached its modern distance. It is one of the earliest, strongest fingerprints of that ancient gravitational bond. And so, the story of the moon's closeness is also the story of our own planet's formation. A world and its satellite, born from the same violent beginning, shaping each other across eons. The outward drift we observe today is not new. It is the continuation of a dance that began in fire and ended in the quiet stability of the modern sky. But as the moon drifted outward and Earth settled, another mystery formed. What forces continue to push the moon away even now, long after the chaos of early Earth has faded? That question carries us into the next part of our journey. Part 4. The tides that push the moon away. Every tide is more than water moving. It is energy shifting, Earth slowing, and the moon responding. As oceans bulge toward and away from the moon, friction with the turning Earth drags those bulges slightly ahead of the moon's orbit. That offset acts like a gravitational handle, pulling the moon forward and outward, bit by bit. A mechanism NASA often describes as one of the universe's slowest engines. To understand this slow engine, you must begin not with water, but with the rotation of our planet. Earth spins once every 24 hours, but the moon takes 27.3 days to orbit us. Because Earth turns much faster, the tidal bulges cannot sit directly beneath the moon's gravitational pull. They are carried slightly ahead, like a wave pushed forward by a moving hull. This slight lead, just a few degrees, creates the conditions for a long gravitational conversation, one that has been happening for billions of years. The physics of this process is simple, yet profound. Earth is rotating eastward. The moon is orbiting more slowly. The tidal bulge, dragged forward by Earth's rotation, pulls on the moon, giving it a tiny forward nudge. And in space, a forward nudge means a higher orbit. That is why the moon drifts away. It is not floating freely. It is being pushed constantly and gently by the energy dissipated through Earth's oceans and crust. Every rising tide, every falling tide, every gentle slosh of water along a coastline is part of this ancient transfer. To appreciate how subtle and relentless this process is, imagine watching the Earth-Moon system in extreme fast motion. You would see the oceans rise and fall like breathing. The Earth would spin like a slowing top, and the moon, once locked in a tight embrace, would spiral steadily outward, expanding its orbit millimeter by millimeter. The dance would look serene, but every step would be driven by friction and gravity working in perfect coordination. Tidal friction arises because Earth is not a perfectly smooth sphere. Its oceans drag along continental shelves, push through narrow straits, and collide with landmasses that interrupt the flow. This friction converts some of Earth's rotational energy into heat, tiny amounts. But not insignificant across long spans of time, the energy removed from Earth's rotation must go somewhere. Nature never allows energy to simply disappear. It becomes the moon's gain. By receiving that energy, the moon climbs outward, increasing its orbital distance. The process is slow enough that you'll never see a change across your lifetime. But the laser reflectors left on the lunar surface by Apollo astronauts reveal the truth. We measure the moon's retreat with centimeter precision, and each year, the data paints the same quiet picture. The moon is slipping gradually away. To truly grasp the scale of this engine, consider how deep its influence runs. The tides you witness along coastlines, gentle ripples or crashing waves, are merely the surface expression of a complex internal process. The real energy exchange happens beneath the waters. It happens in the friction between ocean currents and the seafloor, in the swirl of water around continental margins, and in the subtle rise and fall of solid ground, a phenomenon known as solid Earth tides. Yes, the solid Earth itself flexes slightly under the pull of the moon. The crust lifts and falls by centimeters. That motion, too, contributes to the energy transfer, even though we rarely notice it. As the tides shift, Earth's rotation gradually slows, not dramatically, but detectably. Atomic clocks can measure the lengthening of each day, showing that our 24-hour period is not fixed. Earth is slowly giving up its spin. If you go back hundreds of millions of years, fossil corals and ancient sediment layers reveal more dramatic differences. Some coral formations preserve daily growth bands, like rings in a tree, which allow scientists to count how many days existed in a year at that time. These records show that during the Devonian period, around 400 million years ago, a year held about 400 days. That means each day was roughly 21.8 hours long. This evidence tells the same story. Earth's rotation is slowing and the moon is drifting away. But the story is richer than simple drift. The tides themselves change as the moon retreats. When the moon was closer, tides were colossal, towering surges that could have reshaped continents. As the moon moves outward, the tides weaken, losing a small amount of amplitude with each passing millennium. The gradual reduction in tidal height influences the mixing of ocean waters. It affects how heat moves through the seas, influencing global climate in subtle ways. It shapes ecosystems that rely on tidal rhythms, salt marshes, coral reefs, mangrove forests, and countless species that navigate the boundary between land and water. Even human timekeeping reflects this influence. The ancient desire to understand tides led early astronomers to track lunar cycles, eventually shaping calendars and navigation systems. The moon's retreat, though invisible to the eye, has quietly altered the tides that seafarers, farmers, and coastal communities have relied upon for thousands of years. When you think of tides, it's easy to imagine only the motion of water. But water is simply the visible part of a deeper mechanism. Inside Earth's mantle, tidal forces also cause slight heating and movement. The solid planet stretches and relaxes under the moon's pull, though far more subtly than the oceans. Geophysicists study these rock tides with precise instruments, finding that Earth's crust can rise and fall by as much as 40 centimeters in some regions. All of these motions, oceans rising, crust stretching, mantle shifting, are connected by gravity's quiet insistence that nothing exists in isolation. Earth moves the moon moves Earth. Every motion produces another. It is this feedback loop that powers the retreat. And yet, this loop won't continue forever. As Earth continues to lose rotational energy, the moon's outward drift will eventually slow. Tidal friction will become less effective as the moon moves farther away and the tides grow gentler. Billions of years from now, Earth and moon may reach a point of mutual tidal locking, where one side of Earth will always face the moon, and the moon, as always, will face Earth. At that distance, the tides will be much weaker. The transfer of energy will decline to nearly zero. The outward drift will stop. The system will reach equilibrium. But long before that moment, the sun will evolve and change the gravitational balance of the Earth-Moon system. Its swelling atmosphere during the red giant phase may alter Earth's orbit dramatically, disrupting the quiet tidal engine altogether. The moon's future is tied not only to Earth, but to the life cycle of the sun. For now, though, the engine continues. Every wave, every rising tide, every subtle shift of the oceans carries a whisper of the same ancient force. And even though the moon's escape is measured in centimeters per year, the effect is cumulative, stretching across geological epochs with unwavering precision. The tides that push the moon away are not dramatic. They are not violent. They are steady. They are patient. They are one of the most delicate, reliable energy exchanges in the entire cosmos. And yet, as this slow engine continues, we are left with a deeper question, one that reaches back into the moon's earliest history and forward into its far future. What deeper, invisible force anchors the Earth-Moon system, ensuring that despite all change, their dance never breaks? That is where our next chapter leads. Part 5. How laser beams proved the moon's escape. In 1969, astronauts placed mirrors on the lunar surface. Today, scientists fire lasers at those reflectors and measure the time it takes for the light to return, only a few seconds, but precise enough to detect millimeters of change. These experiments revealed the moon's outward drift with stunning clarity, confirming theories that had existed for centuries and proving, beyond doubt, that the moon is slipping away year after year. To appreciate just how extraordinary this experiment is, you first have to imagine what it means to send a pulse of light across 384,000 kilometers of space, have it hit a small array of mirrors the size of a book, and return home carrying information written in its travel time. The round trip takes about 2.5 seconds, but inside those 2.5 seconds is the record of one of the slowest, most delicate motions in the solar system, the moon's gradual retreat. This technique, lunar laser ranging, sounds like science fiction, but it relies on remarkably simple physics. A laser beam leaves an observatory on Earth traveling at the speed of light. It spreads slightly as it travels, turning into a wide, faint cone by the time it reaches the moon. Only a tiny fraction of the photons strike the retroreflector arrays left by Apollo 11, Apollo 14, and Apollo 15. Because these reflectors are made of corner cube prisms, glass blocks designed so that light entering them is reflected directly back toward the source. The photons that hit them come straight home. Detecting that return is not easy. The beam that left Earth is bright, strong, and coherent. The beam that returns is faint enough that only a few photons reach the detector. Yet those photons are all the scientists need. By measuring precisely how long they took to travel the round trip, they can compute the exact distance between Earth and the moon to an accuracy of a few millimeters. Over days, the distance appears to change because of the moon's elliptical orbit. Over months, the variations follow predictable cycles. But over decades, a subtle trend becomes impossible to miss. The average distance between Earth and moon is increasing by about 3.8 centimeters each year. This is the moon's escape, written not in mythology or imagination, but in pure data. The idea that the moon might be retreating is not new. Centuries ago, long before lasers, scientists studying ancient eclipses noticed small discrepancies between the recorded positions of the moon and predictions based on constant orbital speed. Some suspected that Earth's rotation must be slowing slightly over time, and if Earth slows, the moon should drift outward to conserve angular momentum. But these early hints were uncertain, buried in historical ambiguity, observational limitations, and incomplete models. Lunar laser ranging changed everything. It provided a clean, direct measurement, untouched by human error or ancient records. For the first time, scientists could observe the Earth-Moon distance as it changed in real time. This wasn't just a test of lunar motion, it was a calibration of some of the deepest laws of physics. Einstein's theory of general relativity predicts how bodies move in curved spacetime, and lunar laser ranging provides one of the most precise tests of his equations ever performed. The motion of the moon, its orbit, its drift, its tiny deviations as it responds to gravitational influences, is measured with exquisite detail. These measurements confirm general relativity to astonishing accuracy. But perhaps the most poetic part of this process is its simplicity. Light leaves Earth, light touches the moon. Light returns home with a message about distance, motion, and time. This constant dialogue between Earth and moon continues every day and every night. Weather conditions might obscure the beam, clouds might dim the sky, but observatories around the world, all participating in the lunar laser ranging experiment, send pulses whenever they can. The moon is always there, waiting, holding up its mirrors to the dark. The reflectors left on the lunar surface require no maintenance. They do not degrade. They do not require power. They simply sit there, reflecting light back to Earth as faithfully today as they did more than half a century ago. It's remarkable that an experiment so straightforward can measure something so grand. But that is the beauty of physics. Sometimes, small tools reveal immense truths. As the data accumulated, the pattern became unmistakable. The moon is moving away. The exact rate varies slightly over time because Earth's oceans aren't constant. Tidal friction depends on the shape of the continents, the depth of ocean basins, and the patterns of currents and resonances across the globe. During certain geological periods, the retreat may have been faster or slower. But the long-term trend is consistent. Outward, always outward. Earth's day lengthens as a consequence. The moon lives in a higher orbit, and the Earth-Moon system gradually loses rotational energy while preserving total angular momentum. Lunar laser ranging also allows scientists to study the interior of the moon. By analyzing subtle variations in the moon's motion, researchers can infer whether its core is solid or liquid, how its mantle behaves, and how its crust responds to Earth's tidal forces. In this way, the laser beams act not just as distance probes, but as diagnostic tools, X-rays of an entire world. The experiment also reveals how Earth moves. As the laser beam travels, it must account for Earth's rotation, its movement around the Sun, tectonic drift, atmospheric distortion, and even relativity. The return signal carries information about the precise location of the observatory at the moment the photon arrived. Over years, these measurements contribute to our understanding of how Earth's crust shifts and flexes. There is something quietly profound about this. A beam of light tells us how continents drift. A photon teaches us how planets slow. A laser bounce shows us how moons escape. It is a reminder that even in the vastness of space, the most delicate motions can be measured with patient attention. The reflectors have also become silent witnesses to changing technology. Modern lasers are more powerful and precise than those used in the 1970s. Detectors are more sensitive. Computers calculate distances faster and incorporate more complex corrections. Yet the fundamental method remains unchanged: a beam of light, a mirror, a return. In a universe filled with complexity, this experiment feels like a whisper. A simple question asked repeatedly: how far are you now? And the moon, with perfect consistency, answers with its faint silver echo: a little farther than before. The moon's drift, confirmed by these laser pulses, is one of the most profound demonstrations of the interconnectedness of Earth and its satellite. It shows us that tides are not just shorelines rising and falling, but engines of cosmic motion. It reveals that Earth is not perfectly stable, but always changing in ways we cannot feel. It reminds us that the moon, so familiar and constant in our sky, is slowly slipping away. And what the laser beams prove with precision, the rest of the cosmos confirms in principle. Gravitational systems evolve. Orbiting bodies exchange energy. Worlds shape each other through invisible forces, and those forces ripple across billions of years. As we look toward the next chapter, one question emerges naturally from this discovery: what does Earth lose as the moon drifts away? Because every outward step the moon takes comes at a cost, and that cost is time itself. That is where our story continues. Part 6: What Earth Loses as the Moon Leaves. As the moon drifts outward, Earth pays the cost not in distance but in time. Our planet's rotation slows, lengthening the day by fractions of milliseconds each century, a change recorded in ancient sediment layers and verified by modern atomic clocks. The moon steals a tiny bit of Earth's spin with each passing year, stretching our days ever so gently toward the future. This trade, spin for separation, is one of the quietest, most elegant exchanges in the celestial world. Every rising tide, every falling tide, every slight flex of Earth's crust represents a transfer of rotational energy from the planet to its companion. It is a process so slow you will never sense it, yet so steady it shapes the rhythm of our world across millions of years. If you could compare a modern day to a day in the time of the dinosaurs, you would notice the difference. During the late Cretaceous period, around 70 million years ago, a day was roughly 23 hours and 30 minutes. Go back farther, to the early Paleozoic, more than 400 million years ago, and a day lasted about 22 hours. And earlier still, when complex life had barely begun to take shape, Earth spun even faster, completing a rotation in just 21 hours. These numbers aren't guesses, they are etched into the fossil record. Certain ancient corals, known as rugose corals, laid down daily growth bands, microscopic layers of calcium carbonate deposited one after another as the coral responded to sunlight. These daily layers, stacked into thicker monthly and yearly bands, allow scientists to count how many days existed in one ancient year. From these counts, researchers discovered that in the Devonian period, about 400 million years ago, there were roughly 400 days in a year. This means Earth rotated 400 times while it completed a single orbit around the Sun. Today, we count 365. The reason for the difference lies in the Moon's retreat. Each outward step the Moon takes slows Earth's spin by a tiny amount, causing the length of a day to grow. The change is small, milliseconds per century, but across geological epochs, it accumulates into hours. In this sense, Earth's history is written not only in rocks and fossils, but in time itself. Even now, this slow lengthening continues. Modern atomic clocks, far more precise than any mechanical device, are sensitive enough to detect the gradual drift between the length of a solar day and the standardized second. Every year or two, the world's timekeeping agencies must add a leap second to realign Coordinated Universal Time, UTC, with Earth's slowing rotation. It's a small reminder that the planet turns less steadily than we imagine. This slowing is not uniform. It fluctuates based on how Earth's oceans redistribute mass, how ice melts or grows, and how deep mantle currents shift beneath the crust. A large earthquake, by subtly redistributing the planet's internal mass, can speed up or slow down Earth's rotation by a few microseconds. But the Moon's influence is the dominant long-term trend, pulling Earth towards slower and slower days. As the days lengthen, the physics behind this process remains beautifully simple. Earth spins quickly, the Moon moves slowly, tides bulge, friction drags, energy shifts, Earth's rotation weakens, the Moon's orbit expands, but Earth loses more than rotational speed, it loses stability. One of the Moon's most important roles is to steady Earth's axial tilt, the angle between Earth's rotational axis and the plane of its orbit around the Sun. This tilt, currently 23.4 degrees, is responsible for our seasons. It determines how sunlight falls across the planet, shaping climate zones and long-term weather patterns. Without the Moon's stabilizing mass, Earth's tilt could wobble far more dramatically, shifting over tens of thousands of years between gentle, minimal tilt and extreme lean. Such variations could plunge the planet into harsh ice ages or leave it in prolonged warm periods. Scientists can model what would happen if the Moon were suddenly removed. Without its gravitational anchor, Earth's tilt could wander chaotically, perhaps swinging between 10 and 50 degrees over long intervals. With a 10-degree tilt, the seasons would weaken, leaving the poles in permanent cold and reducing the diversity of climates across the globe. With a 50-degree tilt, the seasons would become extreme: hot summers, brutal winters, and intense variations in sunlight. Life would adapt, of course, but the world would be unrecognizable. As the Moon drifts farther from Earth, its stabilizing effect weakens, though very gradually. The tilt will slowly become more sensitive to gravitational nudges from other planets, especially Jupiter. These changes are subtle over short periods, but across millions of years they influence cycles of ice ages, desert formation, and global climate evolution. In a very real sense, the Moon's retreat changes the tempo of Earth's climate. But there are even more consequences of Earth's slowing rotation. A longer day changes the way heat is distributed on the planet. With slower rotation, the contrast between day and night becomes more pronounced. Daylight lasts longer. Nights stretch out. Deserts may become hotter. Rainfall patterns could shift. Weather systems, which depend on Earth's rotation for their structure, would gradually reorganize. The Coriolis effect, the force that bends winds and shapes hurricanes, weakens as Earth spins more slowly. Storms could form differently, jet streams might drift, entire climate zones could migrate. All of this unfolds over immense spans of time, not across centuries or millennia, but over tens and hundreds of millions of years. Still, the transformation is real, already underway, and guided by the simple fact that the Moon is leaving us. Earth also loses another subtle but important property: rotational energy. Though we seldom think about it, Earth's spin helps maintain the planet's slightly flattened shape. The faster a planet spins, the more it bulges at the equator. As Earth slows, its equatorial bulge decreases ever so slightly. This change is tiny, but detectable with modern instruments. The shift affects ocean circulation, sea level distribution, and even the crust's long-term stress patterns. Mountains rise differently, basins sink at different rates, tectonic plates feel the effects of a world gradually changing shape. It is astonishing that something as delicate as lunar drift could ripple through so many layers of Earth's behavior. But that is the beauty of orbital mechanics. Small forces acting steadily shape entire planets. What Earth loses, the Moon gains. The Moon rises higher, its orbit grows longer, its month stretches, and Earth's day continues to slow. Eventually, billions of years from now, Earth will rotate so slowly that one side will always face the Moon, just as one side of the Moon always faces Earth today. This is called mutual tidal locking, and it represents the final stage of the Earth-Moon evolution. In that far future, a day on Earth might last more than 1,000 hours. The tides will be weaker, the seasons may be different, and Earth's sky will hold a moon much smaller than the one we see now. But long before that equilibrium arrives, the sun's red giant phase will reshape the entire system. Earth's orbit will shift. The moon's retreat may stall or reverse. The delicate exchange of energy that has lasted for billions of years will enter a new chapter far beyond our world's present stability. For now, though, the change is quiet. A few milliseconds here, a gradual drift there, a whisper of motion written into the oceans, the crust, and the sky above. As the moon slips slowly away, Earth loses its spin, its stability, and its familiar rhythm of time. And each of those losses leads us deeper into the next mystery. What happens to the tides themselves as the moon continues its slow departure? That is where our journey goes next. Part 7. The changing rhythm of tides. Tides will not always look the way we know them now. As the moon drifts away, its pull on our oceans weakens, and the tides shrink slowly across geologic time. The great tidal forces that once stirred Earth's young oceans, perhaps even influencing early life, will someday fade into more gentle swells, barely noticeable across the coastlines we know. To understand this slow transformation, imagine the tides not as the waves that lap against a beach, but as planetary-scale rhythms, vast movements of water shaped by gravity, rotation, and time. Modern tides feel predictable to us. We know when they rise, we know when they fall. We sense their strength along bays, harbors, and open coasts. But these patterns are temporary. The tides we know today are just a moment within a much longer tidal story, one defined by the gradual weakening of the moon's gravitational grip. For billions of years, tides were far more powerful. When the moon was closer, the oceans surged with unimaginable force, rising and falling by hundreds of meters. These extreme tides churned ancient coastlines, eroded rocks, and may have played a role in the chemistry of early life. As water rushed inland and then retreated, it delivered nutrients, mixed sediments, and created shallow, sunlit pools, conditions that may have been crucial for the earliest biological reactions. Over time, though, as the moon drifted outward, those tides shrank. The world cooled, continents settled, the oceans calmed. Today's tides are modest by comparison, typically rising just a few feet in most places, with larger tidal ranges only in geographically funnel-shaped regions like the Bay of Fundy. But even these modern tides are already weakening. Each year, the moon's retreat softens its gravitational pull just slightly, and that tiny reduction accumulates across the ages. If you could speed up Earth's geologic future, you would watch the tides diminish slowly. The daily rise and fall along familiar coastlines would flatten. The lines of foam pushed by incoming surf would reach shorter and shorter distances. The great tidal estuaries that have defined ecosystems for millennia would shift, shrink, and eventually settle into far gentler patterns. This weakening is not just a matter of height. Tides influence how heat flows through the oceans, how nutrients circulate, and how ecosystems breathe. On a calm day, the ocean looks still, but beneath the surface, tidal currents carve pathways through the deep. They stir cold, nutrient-rich waters upward and pull warm, sunlit waters down. This mixing drives marine productivity, shapes climate patterns, and connects systems across the globe. As the moon moves farther away, those deep currents will lose power. The ocean will mix less efficiently. Stratification, layers of water separated by temperature and salinity, will increase. Warm layers will remain warm. Cold layers will remain cold. The boundaries between them will sharpen. This shift will influence global climate. Tidal mixing helps regulate Earth's temperature by transporting heat from the equator toward the poles and circulating cold water upward from the depths. With weaker tides, polar regions may cool more dramatically while equatorial waters warm. Ocean currents may slow. The overall circulation of the seas, the global conveyor belt, could gradually rearrange itself. This won't happen quickly. Millions of years will pass before such changes become profound. But the seeds of that future are being sown today. With every millimeter the moon drifts outward. The ecosystems shaped by tides will also change. Salt marshes, for instance, depend on the daily rise and fall of seawater to bring nutrients inland and flush waste back out. Mangrove forests rely on cyclical flooding. Intertidal zones, some of the most biologically rich environments on Earth, exist precisely because tides expose and cover rock surfaces each day. As tides weaken, these zones will shrink. The rhythm of life along coastlines will slow. Species that depend on strong tidal flows may retract or disappear. New species may take their place, adapted to calmer waters and gentler cycles. Human history, too, has been written by tides. Ancient maritime cultures timed their journeys by the ocean's pulse. Modern shipping lanes, fishing grounds, and coastal cities all rely on the predictability of tidal motion. A weaker tide will change coastal navigation, sediment transport, erosion, and flood patterns. Harbors built today may not behave the same way tens of millions of years from now. But just as the moon's retreat weakens tides, Earth's changing shape also influences them. As Earth's rotation slows, its equatorial bulge gradually decreases. This subtly changes the depth of ocean basins and the shapes of continental shelves, both critical factors in tidal amplitude. Because tides interact with the contours of Earth's crust, even minor changes in basin geometry can produce major shifts in tidal behavior. There's also the influence of resonance. Certain ocean basins have natural frequencies, like musical instruments, that can amplify tide heights when conditions align. The Bay of Fundy, for example, experiences some of the world's largest tides because the basin's natural oscillation matches the timing of lunar tides. As the moon drifts outward, the timing of tidal forces will gradually shift, detuning these resonances. Tidal giants like Fundy may shrink in amplitude over the distant future, settling into quieter rhythms. The long-term fate of tides is tied not only to the moon's drift, but to Earth's geography. Continents move, seaways open and close, entire ocean basins appear and vanish. When the supercontinent Pangaea existed 300 million years ago, Earth's tides were very different from today's, shaped by a single vast ocean. Future supercontinents will create new tidal patterns that may either amplify or diminish tides temporarily, depending on their shapes and positions. Yet, through all continental cycles, the underlying trend remains the same. The moon's gravitational pull is weakening, and the tides long-term will diminish. This weakening carries a quiet beauty. It reminds us that even the most familiar aspects of Earth, the gentle rise and fall of the sea, are not permanent. They are shaped by cosmic relationships, by ancient impacts, by the soft physics of friction and motion. The tides we know are only one chapter in a very long story. As the tides fade, Earth will gradually shift toward a calmer, more still-seeming ocean. Shorelines will change more slowly. Waves will rely more on winds than on lunar tides. The rhythm of the sea will feel quieter, more subdued. But this future also poses a question. What happens to life, on land, in water, and along coastlines, when the planet's most ancient beat begins to fade? Scientists believe early life may have been shaped by strong tidal cycles. The repeated flooding and drying of coastal regions could have concentrated organic molecules, providing prime conditions for early chemistry to gather, react, and evolve. As tides weaken across geologic time, the environmental pressures on life change as well. Species evolve in response to new rhythms, gentler tides, longer days, more stable coastlines. Even if humanity is not present in that distant future, life will adapt to the slower pace. The Earth will find a new equilibrium. The oceans will continue to breathe, but in softer, more measured patterns. The Moon's departure, though nearly invisible to us, is writing a new chapter for our planet's future seas. The tides are fading, and with their slow decline comes a deeper question, one that connects energy, motion, and orbital dynamics. If the tides weaken, how does this transformation affect Earth's long-term stability and the very tilt of its axis? This gentle mystery leads us into the next part of our journey. Part 8. How the Moon's distance shapes. Earth's tilt. Earth's axial tilt is not fixed. It wobbles and shifts over thousands of years, but the Moon acts as a stabilizing weight, reducing those variations and softening climatic extremes. As the Moon moves farther away, that stabilizing influence weakens, and Earth's tilt may become more chaotic, altering seasons, weather patterns, and long-term climate cycles in ways we're only beginning to understand. To feel the significance of this, imagine Earth as a spinning top. When a top spins quickly, its axis stays upright. It is steady, balanced, resistant to wandering. But as it slows, the top begins to wobble, its axis drifting in slow circles, tipping this way and that. Earth behaves in a similar way. Right now, our planet spins fast enough that its tilt remains relatively stable, oscillating gently over tens of thousands of years. But this stability is not only due to Earth's rotation, it is due to the Moon. The Moon's gravity pulls on Earth's equatorial bulge, acting like an anchor that dampens how freely Earth's axis can wander. Without the Moon, Earth would tilt much more dramatically. And tilt is not a small detail of planetary behavior. It is the architect of climate. Earth is tilted 23.4 degrees relative to its orbit around the Sun. That angle gives us seasons, the warmth of summer, the softness of spring, the low-angled light of winter. A different tilt produces a different world. If Earth tilted more deeply, the seasons would grow extreme, summers would scorch, winters would deepen. If Earth tilted less, the seasons would fade, the poles would cool permanently, and ice might stretch far into the continents. Because tilt is so important, the Moon's role as a stabilizer has shaped Earth's entire climate history. For billions of years, the Moon has kept Earth's tilt oscillating within a narrow range. Those slow cycles, known as Milankovitch cycles, helped pace the rise and fall of ice ages, influence ocean currents, and regulate the spread of continents and ecosystems. But this stability depends on one quiet fact. The Moon must be close enough to hold Earth steady. As the Moon drifts outward, its stabilizing torque weakens. The gravitational grip that suppresses chaotic wobbling relaxes slowly. Earth becomes a little more susceptible to nudges from other forces, subtle gravitational tugs from Jupiter, Saturn, and the Sun, shifts in internal mass due to plate tectonics, long-term changes in the distribution of oceans and ice. Over millions of years, these small influences can grow. To understand the scale of this, consider Mars. Mars has no large moon to anchor its tilt. As a result, Mars's axial tilt varies wildly, from as little as 10 degrees to more than 60 degrees over long timescales. During periods of high tilt, Mars's poles receive so much sunlight that they warm and release carbon dioxide, altering its thin atmosphere. During periods of low tilt, the poles freeze and its climate shifts dramatically. Earth, protected by the Moon, avoids such chaos. But as the Moon moves farther away, Earth may become more Mars-like in its long-term tilt behavior. This does not mean Earth will suddenly flip over or tilt catastrophically within human lifetimes. The process unfolds over millions of years, too slow to be perceived day by day. But if you could compress Earth's future into a time lapse, watching eons pass like seconds, you might see the axis wobble more widely, wandering through arcs of tilt that reshape climate in powerful ways. A more chaotic tilt could bring cycles of extreme warming and cooling. Some eras might see summers far hotter than today's, with polar regions melting more dramatically. Other eras might plunge vast regions into deep glaciation as the poles tilt farther from the sun. Rainfall patterns would shift, monsoons could strengthen or weaken, deserts might migrate. The band of tropical rainfall, defined by the tilt and heating of the equator, could drift north and south unpredictably across geological epochs. Ocean currents, too, respond to tilt. The angle at which sunlight warms Earth determines temperature gradients between the equator and poles. A larger tilt exaggerates these differences, intensifying currents like the Gulf Stream. A smaller tilt flattens them, slowing circulation and altering the transport of heat around the world. In this way, the moon's retreat quietly shapes Earth's climate future. But there's more to the story of tilt than stability and climate. Tilt also influences long-term habitability. Astrobiologists often consider axial stability when evaluating whether distant exoplanets might host life. Planets that tilt wildly experience extreme climate swings that can challenge the evolution and persistence of life. Stable tilt, by contrast, offers long-term climate predictability, a gentle rhythm in which complex ecosystems can flourish. Earth has enjoyed that stability precisely because of the moon. Its gravitational presence has kept our axis balanced, allowing stable oceans, consistent seasons, and reliable climate patterns to endure for billions of years. As the moon retreats, this stabilizing effect diminishes, but not immediately or catastrophically. Earth will not suddenly become uninhabitable once the moon moves a few thousand kilometers farther away. Instead, the changes happen slowly, so slowly that ecosystems and species have time to adapt, evolve, migrate, and reshape their environments. Life has responded to shifting climate cycles many times. The great ice ages advanced and retreated. Warm periods spread forests across continents. Dry periods expanded deserts. Through all this, life shifted with the planet's tilt. But as the moon continues its slow outward journey, the range of tilt variation will widen. Climate cycles may grow longer and more pronounced. This will influence everything from ocean chemistry to atmospheric circulation to the distribution of plant and animal life. The next question becomes, how far will the moon drift before its stabilizing effect becomes negligible? Based on current measurements, the moon moves away at roughly 3.8 centimeters per year. At that pace, in a billion years, it will be tens of thousands of kilometers farther from Earth. Its ability to dampen axial chaos decreases proportional to the inverse cube of its distance, a steep drop-off. This means that even modest increases in distance lead to significant declines in stabilizing force. At some point in the deep future, hundreds of millions or perhaps billions of years from now, Earth's axis may wander more freely. Simulations suggest that, without the moon's anchoring influence, Earth's tilt could vary between 10 and 45 degrees over geologic time. This range is far larger than today's gentle oscillations and would lead to more dramatic climatic shifts. Yet, in the distant future, the sun will become a dominant factor. As it ages and brightens, the added heat may overshadow the effects of tilt. Earth's climates will be reshaped by solar evolution long before axial chaos reaches its full potential. Still, the moon's retreat contributes to this distant story. It is a quiet loosening of a gravitational bond that has kept Earth steady for eons. There is something quietly poetic about this. The moon, which once loomed enormous in our ancient sky, steadied the Earth through its formative ages. It anchored the seasons, softened extreme climates, and allowed long periods of environmental predictability. Now it is drifting away, and the stabilizing gift it once gave is slowly fading. Earth will adapt as it always has. The climate will shift, ecosystems will evolve, the axis will tilt and retilt, responding to forces that guide the motion of worlds. But the moon's departure sets the stage for a more dynamic, less predictable Earth, a planet shaped not only by its own spin, but by the absence of the silent companion that once held it steady. And this raises a deeper question as we move forward. If Earth's tilt grows more chaotic, what will happen to the length of days and the rhythm of time itself as the moon continues its quiet retreat? That is where our journey leads next. Part 9. When Earth will become tidally locked to the moon. Just as the moon shows only one face to Earth, One day, Earth will show only one face to the moon. Tidal friction doesn't stop. It continues slowing our planet's rotation. Billions of years from now, Earth will rotate so slowly that one hemisphere will forever face the moon, while the other will never see it again. A future predicted by the same physics that locked the moon long ago. To imagine this far future, you have to first understand what tidal locking really is. It is not a sudden event. It is not a catastrophic snap or an abrupt halt. Tidal locking is a gradual surrender, one world's rotation slowing until it aligns perfectly with the orbital rhythm of the body that tugs on it. It is the end result of an ancient gravitational conversation. The moon reached this state billions of years ago. When it first formed, the moon spun rapidly. Its day lasted only a few hours, but Earth's overwhelming gravity raised tides inside the moon's interior, stretching, flexing, heating it. That stretching created friction, and friction drained the moon's spin energy. Slowly, its rotation slowed until one side always faced Earth. And once that lock formed, it remained permanent. The same process is happening to Earth now, just at a different scale and over much longer timescales. Tidal friction within Earth's oceans and crust steals a tiny fraction of rotational energy every day. This lost spin reappears as the moon's outward drift. But as Earth slows, the effects accumulate. The planet's days grow longer. The length of time it takes for Earth to rotate gradually approaches the length of time it takes for the moon to orbit. That is the moment of tidal locking. Right now, Earth's day is about 24 hours, and the moon's orbital period is about 27.3 days. The two rhythms are far apart, but every century, Earth's rotation slows by a few milliseconds, and every year, the moon moves a few centimeters farther away. Over immense spans of time, billions of years, these small changes converge toward equilibrium. In the distant future, Earth will rotate once every 47 days, matching the moon's orbit at that time. At that moment, Earth will stop changing its orientation with respect to the moon. One hemisphere will forever face the moon. The other will live in permanent moonlessness. Imagine what that would look like. On the moon-facing side, the moon will hang at a fixed point in the sky, never rising, never setting, forever suspended above the horizon like a silent companion. Its phases will no longer change. Its shape will no longer wax or wane. It will simply be there, a permanent, unblinking world. On the far side of Earth, the moon will never appear at all. Entire generations of future beings, if they exist then, may grow up on a hemisphere where the moon is not part of the sky, not part of culture, not part of memory. But the consequences go deeper than scenery. When tidal locking occurs, Earth's rotation slows dramatically. A day will no longer last 24 hours. It will last more than 1,000 hours. The rhythm of light and darkness will reshape ecosystems in ways we can barely imagine. For the moon-facing side, the long day-night cycle will disappear entirely. There will be no sunrise or sunset with respect to the moon. But the sun will still rise and set extremely slowly. A single solar day could stretch for weeks. One hemisphere will endure scorching day-length periods, the other long and frigid nights. Patterns of temperature, weather, and climate will evolve into new states. Winds will shift. Ocean currents will reorganize. Rainfall patterns will drift into unfamiliar regimes. Entire biomes will adapt or vanish, depending on how life responds to these immense changes. But there is something else. Something even more subtle and beautiful. As Earth rotates more slowly, its equatorial bulge will shrink. The planet's shape will change slightly, becoming more spherical. This, too, affects the process of tidal locking. A more spherical Earth offers less rotational resistance, helping the lock settle permanently. Yet this future is not guaranteed to happen exactly as we might imagine, because the moon's outward drift will not continue forever. It slows as the moon moves farther away. The tidal forces weaken. Eventually, the outward drift will halt when the Earth-Moon system reaches a perfect balance between tidal friction and orbital distance. But even this balance may never be reached, because something else will intervene first. The sun. In about 5 billion years, the sun will swell into a red giant. Its gravitational influence on Earth will change significantly. Earth may be pushed outward into a wider orbit or pulled inward, destabilizing the Earth-Moon system entirely. The Moon may spiral inward, break apart, or be lost from Earth's gravitational grasp. This means that tidal locking between Earth and the Moon may occur only if the system survives long enough, and if the Sun's transformations don't disrupt the delicate gravitational interplay before equilibrium is reached. But even if the universe devours this future before it arrives, the physics behind tidal locking remains deeply compelling. It shows the mathematical elegance of cosmic relationships. It reveals how even the slowest forces shape worlds, and it gives us a glimpse of what our planet might one day become if the clock of the cosmos were allowed to run without interruption. To understand what life might experience on a tidally locked Earth, imagine watching the sun move through the sky, not over hours, but over days and weeks. A sunrise might last an entire month. The sun would creep upward slowly, warming the land beneath it with unbearable intensity. Forests might adapt by closing their leaves for weeks at a time. Animals might retreat underground during long day periods, emerging only during twilight seasons. The world would divide into 3 climatic zones: a long day zone, a long night zone, and a perpetual dusk ring between them. In the Moon's direction, the sky would be constant. The Moon would hang motionless, a glowing reminder of the slow gravitational dance that shaped Earth's destiny. The dark side, forever moonless, would depend entirely on solar cycles. The absence of lunar tides would reshape coastal ecosystems. Gentle tides might still exist from the sun alone, but they would be faint, barely noticeable compared to the tides we know today. Yet even in this strange future, something familiar remains. Earth and Moon will still be bound. They will still orbit each other. Their gravitational dance will still shape the motion of the seas and the passage of time. Tidal locking is not a destruction of motion. It is the final choreography of a relationship billions of years in the making. And as we look toward this far-off equilibrium, another question naturally emerges from the stillness. What will life be like on Earth when the Moon is twice as far away and the tides and days have transformed beyond recognition? That is where our next chapter leads. Part 10. What happens to life? When the Moon is twice as far, a more distant moon means weaker tides, gentler ocean mixing, longer days, and a slower global rhythm. Marine ecosystems, weather cycles, and even the behavior of coastal life are subtly shaped by the tides. As the Moon recedes, Earth's biological clock, tuned for billions of years to a lunar rhythm, will gradually drift into a new pattern, quiet and unfamiliar. To understand this transformation, imagine watching Earth from orbit, not today, but millions of years in the future. Below you, the oceans still shimmer in sunlight. The continents still breathe with forests and deserts, and storms still spiral across the surface. But the timing of everything feels slower. The world turns more gently. The tides rise with less force. The pulse of the planet has softened. This softness is the first sign of a moon that has drifted farther away. For billions of years, life on Earth has evolved inside a pattern shaped by the Moon's gravitational pull. Every tidal pool, every intertidal creature, every migrating fish, every coral spawning event follows lunar cues with astonishing precision. Biologists call these cycles circulunar rhythms, natural clocks synchronized with the Moon's orbit. Even creatures far from the sea carry the imprint of lunar time. Birds migrate under moonlit cues, insects coordinate mating flights, plants adjust subtle hormonal cycles with the waxing and waning of moonlight. A more distant moon disrupts this, but not abruptly. It happens the same way the Moon's retreat has always happened, quietly, millimeter by millimeter, as though time itself were exhaling. As the Moon recedes, the tides weaken. Intertidal zones shrink. Coastal ecosystems that rely on pulsating rhythms of water begin to reorganize. Consider a tidal flat today. Twice a day, water covers the mud, bringing nutrients, oxygen, and life. Crabs scuttle in with the tide and burrow when it leaves. Plants anchor themselves in sediment that is regularly disturbed. Everything depends on the rise and fall. Now, imagine that rise and fall becoming gentle, too gentle to reach as far inland, too gentle to stir the sediment, too gentle to sustain the same communities. The habitat shrinks. Species that rely on high-energy tides retreat or vanish. New species move in, ones adapted to calmer coastlines, less nutrient mixing, and more stable water levels. The change will be slow enough that evolution can keep pace, but the coastline of the far future will be different, quieter, smoother, simpler. Marine life deeper in the ocean will feel the shift in more hidden ways. Much of the ocean's nutrient cycling is powered by tidal mixing, the churning of water as tides pull warm surface layers over cold, deep ones. This mixing fertilizes the surface, feeding plankton that form the base of the marine food chain. As tides weaken, this mixing fades. The ocean stratifies. Warm layers stay warm. Cold layers stay cold. The boundary between them becomes sharper. In a highly stratified ocean, life must adapt to more rigid boundaries. Nutrient-rich deep waters no longer well up as easily. Plankton blooms become more seasonal, less evenly distributed. Fish migrations follow different paths. Large marine mammals may shift feeding grounds to areas where currents, not tides, create the mixing they depend on. In this future ocean, life does not disappear, but it reorganizes. New ecosystems form, old ones fade. The ocean's heartbeat slows, matching the slowing rotation of the planet. A longer day has its own biological consequences. As Earth's rotation gradually lengthens, from 24 to 25 hours, then 26, then more, circadian rhythms adapt. Most life on Earth, from insects to mammals, follows an internal clock near 24 hours long. This clock evolved because Earth spins once every day, but with the day stretching little by little, these internal rhythms must stretch too. Some species will adapt through natural selection. Others will alter their behavioral patterns. Still others may struggle, especially those whose life cycles depend tightly on sunrise and sunset. Plants, for example, open and close their stomata in response to daily light cues. As daylight lengthens, growth cycles shift, flowering times drift, seed dispersal seasons migrate across the calendar. Agricultural crops, if humans still exist in that distant age, would need to be adapted or redesigned to match the new solar rhythm. Animals respond even more intricately. Birds time migrations based on daylight length. Predators use dawn and dusk to hunt. Nocturnal species rely on the duration of night for their feeding patterns. As nights stretch or days elongate, ecosystems reorganize to match the shifting cadence of sunlight. The weakening of lunar tides also changes the power of moonlight itself. A more distant moon appears smaller and dimmer. Moonlight has always guided nocturnal behaviors, mating patterns, and migration events. But as the moon moves away, its brightness drops. The full moon of the far future will glow less intensely in the sky. Still beautiful, but gentler, with less power to shape ecological patterns. Some species that rely on bright moonlight for mating displays, certain fish, corals, and insects, could adapt by shifting to darker cues or altering their timing. Others may lose these lunar-linked behaviors altogether, drifting into new evolutionary strategies. But perhaps the most profound change comes from Earth's axial tilt. As described in the previous segment, the moon stabilizes Earth's tilt. Once the moon is much farther away, that stabilizing force weakens. A more variable tilt means more extreme climate cycles. Life will have to navigate periods of intense warmth, deep ice, shifting coastlines, and altered climates. These long, slow cycles will profoundly shape evolution. Species will move, adapt, or go extinct in response to shifting habitats. Forests may expand toward the poles during warm periods and retreat toward the equator during cold ones. Grasslands may swell and shrink. Ice sheets might grow thicker during high-tilt epochs, pushing species to migrate or perish. Life has survived such transitions before, but the added variability from a receding moon amplifies these patterns. There's another dimension to consider: the cultural and psychological impact on future intelligent beings, if such beings exist. Humanity built mythologies, calendars, and rituals around the moon. Entire civilizations timed agriculture with lunar cycles, navigated seas by moonlight, and wove stories around its phases. A smaller, dimmer moon, or no visible moon at all on one hemisphere, rewrites the emotional fabric of a species. Where the moon once inspired tide tables, poetry, festivals, and stories, the distant moon might feel like a fainter presence, a relic in the sky, still beautiful but less commanding. And on the moonless hemisphere, there would be no lunar influence at all. No full moon nights, no lunar eclipses, no tides shaped by the moon. The sky would feel emptier. The culture of that hemisphere might evolve without the concept of a moon, without the symbol that shaped so many human ideas about cycles, time, and reflection. If there is intelligent life in that far future, the meaning of night will be different. Yet through all these changes, through the weakening tides, the lengthening days, the shifting ecosystems, the altered light, the connection between Earth and Moon continues. They remain bound. Their gravitational dance continues even as the space between them grows. The moon will still trace the same elegant arc across the sky. Its phases will still cycle, though more slowly. Its influence will still be present, though fainter. And eventually, as Earth grows closer to tidal locking, the relationship between life and the moon will transform entirely. Because if one side of Earth will always face the moon, then half the planet will live under a permanent lunar presence, while the other half will never see it at all. This naturally leads to the next great question in our journey. If life changes as the moon drifts to twice its distance, what becomes of the moon itself and the evidence hidden in its ancient rock? That is where our story continues. Part 11. Could the moon ever escape completely? The moon is leaving us, but the escape is not inevitable. As the sun evolves, its expanding atmosphere and shifting gravitational influence may drastically alter Earth's orbit. Simulations suggest that long before the moon could ever drift far enough to escape, the sun's red giant phase will rewrite every orbit in the inner solar system. The moon's fate, like Earth's, is ultimately tied to the life cycle of the sun. To answer whether the moon could ever break free, we must stretch our imagination across billions of years and look at forces that move with unimaginable slowness. Right now, the moon drifts outward at about 3.8 centimeters per year. At that rate, escaping Earth's gravity would require the moon to travel millions of kilometers farther away, far beyond its current orbit, far beyond the equilibrium distance it will eventually reach. But the moon's outward drift is not constant. It slows over time. As the moon moves farther away, tidal forces weaken. And because tidal forces are the very engine pushing the moon outward, their weakening gradually brings the outward drift to a crawl. Eventually, billions of years from now, that drift will stop almost entirely. The Earth-Moon system will approach a stable configuration known as double synchronous rotation, a state where both Earth and Moon are tidally locked to each other. Earth will rotate once for every lunar orbit. One side of Earth will forever face the moon, and one side will never see it. When this equilibrium arrives, the moon's outward migration will cease. Its escape trajectory will no longer have energy to continue. In other words, under the current laws of gravity and tidal evolution, the moon cannot escape. It will reach a stable orbit long before drifting into the freedom of interplanetary space. But this assumes the sun remains unchanged, and the sun never remains unchanged. To understand the moon's long-term fate, we must look at the sun's own life cycle, a vast story unfolding across billions of years. Right now, the sun is in its main sequence phase, calmly converting hydrogen into helium in its core. This peaceful period will last another 5 billion years. After that, the sun will begin to change in ways that reshape the inner solar system entirely. As the sun ages, it brightens, its luminosity increases, the light that reaches Earth intensifies, warming the oceans and stirring the climate. But brightness is only the first step. Deep within the core, the sun will begin exhausting hydrogen, forcing fusion to shift outward. This transition will destabilize the sun's structure. The outer layers will swell. The sun will balloon into a red giant, growing hundreds of times larger than it is now. swallowing Mercury and Venus and stretching close to or beyond Earth's orbit. When that happens, everything changes. The sun's mass will decrease as stellar winds blow vast amounts of material into space. And when the sun loses mass, its gravitational pull weakens. Planets drift outward, not because they flee by their own will, but because the sun no longer holds them quite as tightly. This outward drift affects Earth and the Moon together. The entire Earth-Moon system will climb to a larger orbit around the sun. But as the sun expands, the outer layers may reach or surpass Earth's orbital path. The question becomes whether Earth spirals inward into the sun or outward fast enough to escape consumption. For the Moon, the danger is indirect. The Moon itself will not be swallowed unless Earth is. Its fate depends on Earth's position. If Earth is engulfed, the Moon will follow. It will fall with us into the sun's expanding atmosphere. The lunar surface, so cold and airless today, would vaporize within seconds. Millennia of craters would fade in a burst of fire. The Moon's long, patient story would end in a moment of stellar heat. But if Earth survives by drifting outward, if Earth slips just beyond the reach of the sun's swollen outer layers, then the Moon survives as well. Yet, even in that case, its orbit may change dramatically. As the sun loses mass, Earth's orbit expands, but the Moon orbits Earth, not the sun. This means the relative distance between Earth and Moon stays the same, but the gravitational context changes. The Moon's orbital period may lengthen. Tidal forces on Earth will weaken even more. The system may settle into a configuration different from anything we can imagine today. Some simulations suggest a possible delicate future. Earth and the Moon drift outward together, surviving the red giant phase, continuing their tidal dance around a dimming sun. The sun eventually sheds its outer layers, becoming a white dwarf, hot but small, glowing in the center of an expanding planetary nebula. In this quiet aftermath, Earth and Moon might remain bound, circling their faint stellar remnant for billions more years. In such a scenario, the Moon still cannot escape completely, not because it is tightly held, but because Earth and the Sun will lose mass together in a way that preserves their gravitational relationship. Other models suggest darker possibilities. As the Sun swells, its atmosphere becomes turbulent, filled with drag forces and chaotic magnetic interactions. This expanding atmosphere may push Earth inward rather than outward. If Earth enters the Sun's envelope, its orbit will decay rapidly. The Moon's orbit, which depends entirely on Earth, would decay with it. Both worlds would be consumed. It is here that the question, could the Moon ever escape, meets a cosmic truth. The Moon's fate is not a question of escape velocity, it is a question of stellar destiny. Even before the sun becomes a red giant, its slow brightening will transform Earth in ways that indirectly affect the Earth-Moon system. Higher temperatures will alter ocean depths and continental shapes. Tidal friction will change. The slowing of Earth's rotation will accelerate or decelerate depending on the new distribution of oceans and ice. All of these secondary effects influence the Moon's drift, but none of them grant the Moon enough energy to break free. The only event that could give the Moon true escape velocity is a dramatic disruption of the Earth-Moon gravitational bond, something far more extreme than tidal physics can produce. A passing star could do it. A massive gravitational encounter could yank the Moon out of orbit, but such events are extraordinarily unlikely in the near future. The solar system is stable, its neighbors are distant. The Moon, for now, is safe. If we define escape as independent motion, drifting alone through interplanetary space no longer bound to Earth, then no, the Moon cannot escape on its own. Not under the familiar laws of orbital evolution, not under the slow push of tides, not under normal solar conditions. Its fate is locked to ours. And that shared fate leads to the next question. What clues about our planet's past, its tides, its heat, its formation, are hidden within the Moon's ancient rock? That is where our journey continues. Part 12. The Ancient Clues. Hidden in lunar rocks are time capsules of tidal history. Isotopes, cooling patterns, and stress lines inside the crust reveal moments when the moon was pulled, stretched, and warmed by tides far stronger than today's. The Grail mission mapped these patterns in exquisite detail, showing how Earth's gravity shaped the moon's interior over billions of years. To understand the moon's past, you must imagine it not as the cold, silent world we see now, but as a world once alive with motion. When the moon first formed, likely from the debris of a colossal impact between proto-Earth and a Mars-sized planet, the newborn moon was molten, glowing, restless. It orbited much closer to Earth, so close that it filled the sky like a second sun. And in that early age, the tidal forces acting upon it were immense. Those tides did not just pull on the moon's oceans, because the moon has none. They pulled on its entire body. The young moon flexed like warm clay, stretching and compressing with every orbit. This flexing generated heat, driving volcanic activity and shaping the crust from the inside out. The traces of that ancient internal motion remain frozen in the lunar rock, preserved for billions of years. Unlike Earth, the moon has no rain, no wind, no oceans, no plate tectonics. Nothing erases its past. Every crater, every crack, every ridge sits untouched, a geological library open to the skies. Because of that, the moon acts as a perfect archive, recording not only its own past but the gravitational history of the Earth-Moon system. Scientists studying lunar samples brought back by the Apollo missions quickly learned that these rocks tell stories. Some carry tiny glass beads formed in fountains of molten lava. Some contain magnetized minerals, hinting at a lunar magnetic field long extinct. Others preserve chemical ratios that can only form during episodes of intense tidal heating. One of the most striking clues comes from isotopic analysis, examining the ratios of certain atoms within lunar minerals. These isotopes reveal cooling rates, exposure histories, and thermal events that occurred as the moon slowly locked to Earth. When tidal forces were strong, they produced heat deep within the moon. This heat left signatures, subtle variations in mineral structure shaped by cycles of stress and relaxation. Geologists trace these patterns like detectives, reading pressure lines and thermal scars as if they were entries in an ancient diary. The cracking of the crust, visible through extensive networks of faults across the lunar surface, is one of the clearest signs of that tidal history. Some cracks align with tidal bulges, the regions of the moon that were repeatedly stretched by Earth's gravity when the moon orbited closer. Others align with ancient, volcanic features, suggesting that tides once fueled eruptions by pumping energy into the moon's mantle. But the most profound revelations came from the Grail mission, the Gravity Recovery and Interior Laboratory. Launched in 2011, Grail used 2 spacecraft flying in formation to map the moon's gravitational field with extraordinary precision. By measuring tiny changes in the distance between the spacecraft as they orbited, scientists constructed a detailed picture of the moon's interior density. What they found was astonishing. Beneath the crust lay hidden fractures, long fossil ridges, and regions where the moon's surface had been stretched thinner by ancient tidal pulling. Some patterns wrapped around the entire globe, evidence of global-scale tidal flexing. Others marked localized deformations, places where tidal heating had created pockets of molten rock billions of years ago. The moon's interior, it turned out, was not a uniform sphere. It was a world shaped like soft clay under the hands of gravity, kneaded into ridges and basins by Earth's immense pull. Grail also revealed evidence of mascons, mass concentrations, beneath the moon's large basins. These dense regions likely formed when molten rock flooded impact craters and cooled unevenly. But their neatly circular patterns also suggested tidal influences guiding the distribution of mass. The moon's gravity itself, mapped with exquisite clarity, became a record of its tidal past. Even the way the moon spins today carries clues. Its synchronous rotation, always showing one face to Earth, was established through tidal friction. And the slight wobble it retains, called libration, is a remnant of the tug-of-war that shaped its early motion. Hidden within that wobble are mathematical echoes of the moon's original spin rate and the strength of ancient tides. But lunar rocks tell another story, one even older, tied to the moon's formation. When the giant impact created the Earth-Moon system, it heated both bodies intensely. The Moon began as a molten ocean of rock. As it cooled, minerals separated and crystallized. Some minerals rose to form a light crust, others sank. The timing of these processes is encoded in the chemical fingerprints of lunar rocks. And here, too, tides played a role. Strong early tides churned the Moon's mantle, circulating heat and causing different regions to cool at different rates. This uneven cooling produced mineral layers that still exist today, layers that scientists can read like rings in a tree. From this, geologists reconstructed a story: a molten moon cooling under intense tidal heating, a surface cracking as stresses built deep below, volcanic eruptions erupting across the near side, a slow settling as tides weakened and the Moon drifted outward. Even the striking difference between the Moon's near side, facing Earth, and far side contains clues. The near side is smoother, filled with dark Maria, vast basalt plains formed by ancient volcanic activity. The far side is heavily cratered with almost no Maria. Why? One emerging explanation is tidal heating. Because the near side always faced Earth, it remained warmer for longer, allowing magma to flow more easily. The far side cooled faster, creating a thicker crust that resisted volcanic flooding. In this sense, every contrast between the Moon's hemispheres is a fossil of Earth's gravitational influence. The rocks that astronauts picked up carry these stories in their internal chemistry. Some contain trapped gases from ancient volcanic eruptions. Others preserve tiny pockets of melt formed by impacts or tidal stresses. Some hold zircon crystals older than any rock on Earth, their atomic structure unaltered for billions of years. Together, these clues reveal not just the Moon's history, but Earth's. Because the Moon formed from Earth's outer layers, its composition mirrors Earth's mantle. The isotopic match between Earth rocks and Moon rocks remains one of the strongest pieces of evidence for the giant impact theory. This shared origin means that studying lunar rocks reveals what Earth's early crust was like, before erosion, weather, and plate tectonics erased the evidence. The Moon is a museum of Earth's ancient self. The tidal scars inside the Moon tell us how fast Earth once spun. The thickness of lunar mineral layers tells us how quickly the Moon cooled, and therefore how close it once was. The patterns of crustal deformation tell us how Earth's gravity dominated the early solar system. Every crack and mineral grain is a whisper from a younger world. And as we decipher these whispers, one question becomes even more compelling. If the Moon carries the story of Earth's past so clearly, what does it tell us about the future relationship between these two worlds, about tides, rotation, and the changing dance of gravity? That is where our journey moves next. Part 13. The far future of the Earth-Moon system. As Earth slows and the Moon drifts outward, their orbits follow a predictable pattern governed by conservation of angular momentum. Eventually, these changes will reach a point of equilibrium if the Sun's evolution doesn't intervene first. Long before that equilibrium is reached, Earth's continents, tides, and even the length of a year will have transformed beyond recognition. To imagine this distant future, you must picture the Earth-Moon system not as two fixed bodies, but as partners in a slow cosmic waltz, one losing rotational energy, the other climbing outward in response. This dance has lasted for more than 4 billion years, and it will continue long after anything familiar has vanished from Earth's surface. Yet even this graceful motion, steady and mathematical, will eventually come up against the limits set by the deeper workings of the solar system. Right now, Earth spins once every 24 hours and the Moon orbits. Earth every 27.3 days, but these numbers are temporary. As Earth loses rotational energy to tidal friction, its days lengthen. Meanwhile, as the Moon steals that energy, it moves away and its orbital period increases. This exchange is governed by angular momentum, a law that ensures the total spin and orbital motion of the system remains constant, even as the individual components shift. If nothing disturbed this arrangement, Earth and Moon would eventually reach a state of double tidal locking. Earth would rotate once for every orbital period of the Moon. The The moon would already show one face toward Earth, as it does now, but Earth, in that far future, would also show one face toward the moon. The two worlds would hold each other in a steady, unchanging gaze. But that equilibrium lies tens of billions of years away, far longer than the sun will survive. So instead of reaching that perfect gravitational balance, the Earth-Moon system will unfold through a series of long, slow transformations shaped by time, continental drift, climate cycles, and stellar evolution. The first major transformation occurs simply through the lengthening of Earth's days. A day will not always be 24 hours. In 200 million years, a day may be closer to 25 hours. In 600 million years, it may reach 26. Before the sun swells into a red giant, a day on Earth could span 30 hours or more. That slow stretching of time affects everything. It changes winds, ocean currents, and the distribution of heat across the planet. It alters biological rhythms, some of which evolved around the steady cadence of sunrise and sunset. It influences weather patterns, storm intensity, and the way energy circulates through the atmosphere. But Earth is changing in other ways too. Continents never stay still. In the next few 100 million years, the continents will drift together once again, forming a new supercontinent. Geologists already have names for these possibilities: Pangaea Proxima, Novopangaea, Amasia. Which one emerges depends on the direction and timing of plate motions, but the result will be the same: one vast landmass surrounded by a single global ocean. Supercontinents dramatically reshape tides. When all land lies together, the resonance of ocean basins changes. Some ancient supercontinents saw enormous tides in certain regions and almost no tides in others. As the moon drifts farther away and tides weaken overall, the formation of a supercontinent could amplify or mute local tidal variations in unpredictable ways. Tides are only one part of this evolving picture. The year itself will change. As the sun slowly loses mass over billions of years, Earth's orbit will expand. A more distant orbit means a longer year. The change is small at first, fractions of a second per century, but across deep time, it becomes significant. The combination of a longer day and a longer year will alter Earth's seasonal rhythms. Some future epoch may see gentler seasons or more extreme ones, depending on Earth's tilt and orbital distance. And Earth's tilt, as we explored earlier, will not remain as stable as it is today. As the moon drifts farther from Earth, its stabilizing influence weakens. This opens the door to larger variations in axial tilt, a shift that could dramatically alter climate cycles. Earth could enter eras of intense warmth followed by deep freezes. Climate belts may wander. Rainfall patterns could drift across continents in ways that reshape entire ecosystems. Yet even these planetary shifts pale beside what happens when the sun begins to evolve. Long before the sun becomes a red giant, perhaps within 1 to 2 billion years, the sun's increasing brightness will heat Earth to the point where oceans begin to evaporate. The moist greenhouse effect will set in. Water vapor will rise high into the atmosphere and break apart under ultraviolet light, allowing hydrogen to escape into space. This slow loss of oceans gradually weakens tides further. With continents baked dry and water levels shrinking, tidal friction dramatically decreases. This means Earth's day lengthens more slowly, which in turn slows the moon's retreat. The dance between Earth and moon continues, but sluggishly, resisting change as the environment fades. In this stage of Earth's future, tidal evolution grinds almost to a halt, not because the physics have changed, but because the oceans themselves, the engine of tidal friction, are gone. Earth becomes a quieter world, a world where the moon still recedes, but at a pace so faint it becomes almost immeasurable. Eventually, the sun will swell. The red giant phase begins. The sun grows hundreds of times larger, its outer layers expanding outward into the solar system. Its gravity weakens as it sheds mass. Earth's orbit widens, but not necessarily enough to escape the sun's reach. The moon's orbit widens as well, but its fate is entirely tied to Earth's. Where Earth goes, the moon goes. If Earth is swallowed by the sun, the moon is swallowed too. If Earth escapes, the moon survives. If Earth spirals inward, the moon spirals with it. Some simulations show that Earth may just barely avoid engulfment, orbiting the outer edge of the Sun's expanded atmosphere. Others suggest Earth plunges in, vaporizing over seconds. Still others show Earth's orbit destabilizing, nudged by resonances with other planets or chaotic interactions within the Sun's bloated envelope. The Earth-Moon system, so predictable for billions of years, enters this final chaotic chapter where certainty dissolves. But even if Earth survives this fiery upheaval, the solar system that emerges afterward, when the Sun has shed its outer layers and become a white dwarf, will be very different. The white dwarf Sun will be small but incredibly dense, with weaker light but intense gravity close to its surface. Earth and Moon, if they remain, will orbit farther out than before. Tidal forces will be weaker, the Moon's outward drift may cease entirely. In this distant, dim future, the Earth-Moon system may finally approach that tidal equilibrium. Nature has been pushing toward since its birth. Earth's rotation may slow to match the Moon's orbit. The Moon may become permanently fixed in Earth's sky. Tides may fade into near silence. It is a peaceful ending, quiet, steady, almost meditative. But the universe rarely allows such perfect balances to last forever. Gravitational nudges from passing stars could perturb Earth's orbit. Interactions with the remnants of other planetary systems could tug at the Earth-Moon pair. The slow, endless dance between these two worlds may continue under a fading sun, or it may be interrupted entirely by the wider tides of the galaxy. In the far future, the Earth-Moon relationship reaches beyond the boundaries of our current understanding. But one thing remains certain. Their story is intertwined until the end. And that connection leads into one final question. What does this long, intricate evolution reveal about the nature of gravity itself and the subtle forces that guide entire worlds? That is where our journey continues. Part 14. How the Moon's retreat once saved Earth. There's a quiet irony in the Moon's slow escape. This drift once stabilized Earth at a critical moment. Had the Moon remained much closer, tidal friction might have torn its crust or destabilized Earth's rotation. Instead, the gradual outward movement created the conditions for long-term climate stability, conditions that allowed life to flourish. To understand this ancient turning point, imagine Earth not as the calm blue world we know today, but as a young, restless planet. The Moon had only just formed from the debris of a colossal collision. It orbited far closer, so close that it would have filled the sky like a vast glowing world. Tidal forces were immense. The planet's oceans heaved like liquid mountains, its crust flexed, its mantle churned with heat drawn upward by the Moon's powerful gravitational pull. This was a dangerous time for a world just beginning to stabilize. Earth's crust was still thin in many places, oceans surged with overwhelming force, and the young planet's rotation, fast and unstable, made the tides even more extreme. Had the Moon remained in that position for too long, the consequences could have been catastrophic. The tides would have continued to whip the oceans into violent cycles, eroding coastlines faster than continents could form them. The crust, stretched and compressed daily, might have fractured more intensely. Volcanic activity could have intensified beyond what life could endure, and the rotation of Earth itself could have destabilized, wobbling wildly under the stress of such enormous tidal bulges. Instead, something remarkable happened. The Moon began to drift outward. That retreat, driven by the same tidal forces that once threatened Earth, was both a release and a rescue. As the Moon moved away, tides weakened. The immense gravitational leverage it once exerted over Earth softened. The planet's crust cooled and thickened, its rotation steadied, and Earth entered a quieter chapter, one where climate cycles became more predictable, continents more stable, and oceans calmer. This stabilization is one of the great unsung gifts the Moon has given Earth. Tides still existed, but they became rhythmic rather than destructive. Earth's axial tilt still varied, but within a narrower, more habitable range. Seasons emerged, weather patterns took shape, ocean circulation began settling into long-term cycles that supported complex chemistry and early life. The Moon's retreat shaped these cycles in ways that might have made the difference between a chaotic, unstable world, and one capable of nurturing biology. To see how dramatic this change was, consider Earth's early day length. Shortly after the moon formed, Earth spun once every 5 or 6 hours. Rapid rotation produced enormous tides that surged across the globe more than 3 times per day. The friction from these tides heated the oceans, warmed the crust, and altered Earth's interior in unpredictable ways. But as the moon retreated, Earth's spin slowed, days lengthened, the tides mellowed, and the rate of tidal friction decreased. This slowdown acted like a planetary brake, allowing Earth's rotation to settle into a more stable rhythm. Because a planet's rotation influences everything from atmospheric circulation to ocean currents, this shift affected every layer of Earth's climate. A slower rotation leads to more moderate winds and calmer global circulation patterns. Storms become less extreme. Temperature gradients flatten. The climate becomes gentler, more predictable. If the moon had stayed closer, Earth's rapid rotation might have produced more chaotic atmospheric patterns, jet streams looping erratically, storms intensifying, and weather cycles becoming more extreme. Life might have struggled to gain a foothold in such an environment, but the moon gently stepping away created a calmer sky. The retreat also shaped Earth's wobble, its axial tilt. As the moon moved outward, its ability to stabilize Earth's tilt changed. Early on, when the moon was close, its stabilizing force was enormous, so strong that it prevented Earth's axis from flipping or wandering wildly during its first billion years. This stability ensured consistent seasons and climate patterns through epochs when early life most needed environmental continuity. Without that stabilizing influence, Earth's tilt could have swung unpredictably, creating catastrophic climate swings, deep freezes followed by extreme heat. Life might never have formed at all. But as the moon moved outward, its stabilizing influence softened at exactly the right pace. It remained strong enough to prevent chaos, but gentle enough to allow the Earth-Moon system to evolve naturally. This rare balance is something planetary scientists marvel at. The moon retreated at just the right speed to calm the Earth without abandoning it. And it wasn't only Earth's surface that benefited. The interior of the planet also changed. Tidal friction once stirred the mantle intensely, driving heat upward. Too much of this heating could have destabilized the crust or triggered excessive volcanism. But as the moon retreated, the mantle cooled at a sustainable pace, allowing plate tectonics to take over. Plate tectonics is crucial for life. It recycles carbon, stabilizes climate, and releases nutrients into the oceans. Earth is the only planet in the solar system with active plate tectonics, and the moon's retreat helped make that possible by easing the early tidal stresses on the crust. Even Earth's magnetic field may owe something to the moon's retreat. A calmer mantle allowed the core to settle into a stable convective pattern, powering the dynamo that generates Earth's magnetic shield. Without it, life would be exposed to harsh solar radiation. So in many ways, the moon's slow departure helped Earth become a planet where life could blossom. But the story does not end there. The moon continued to drift away, steadily, patiently, altering Earth's tides and rotation across geological time. When early life emerged, perhaps 3.5 billion years ago, the moon was closer than today, but not overwhelmingly so. Tides were stronger, yes, but strong tides may have played a role in concentrating organic molecules in shallow coastal pools, accelerating the chemistry of life. By the time complex life evolved, the moon had drifted far enough that tides became gentler, creating stable tidal zones ideal for the rise of early ecosystems, tidal pools, estuaries, and coastal wetlands. When the first plants colonized land, the moon was already at a distance that produced reliable tidal cycles that helped shape coastal climates and nutrient flows. When mammals evolved, the Earth-Moon system had grown even more stable. The moon hung in the sky at a familiar distance, shaping 24-hour rhythms that many species, including humans, built their biology around. In each era, the moon was at just the right distance to help life thrive. This is the quiet miracle of the Earth-Moon system. The moon's retreat has not been a loss, but a gradual tuning of Earth's environment. Too close, and Earth's rotation would be unstable. too far, and Earth's tilt might wander dangerously. But drifting away at the speed it did, and still does, placed the moon in the optimal zone for billions of years of habitability. This balance may be rare in the universe. Most planets lack large moons entirely. Others have moons too small to stabilize them or too massive to avoid destructive tidal forces. Earth's moon is uniquely sized and uniquely distanced. Its retreat is not a flaw, but a feature, one that sheltered Earth when it mattered most. And it leads us toward the next profound question. If the moon once protected Earth by moving outward, what deeper laws of gravity and motion made such a delicate balance possible? And what do they reveal about the future of this ancient partnership? That is where our journey continues. Part 15. Why the moon's departure feels so human. Maybe the moon's slow leaving resonates with us because change often happens this way, quietly, imperceptibly, over years that feel still. The moon has been our companion since long before humans existed, lighting ancient nights, shaping tides, influencing calendars, inspiring stories. To know it is drifting away is to feel the fragility of cosmic relationships, even the ones that feel eternal. There is something deeply human in the realization that the moon is slipping from our grasp, not dramatically, not suddenly, but with the same slow patience that marks many endings in life. It is the kind of change you can only measure not in days or years, but in generations, epochs, and geological ages. The moon does not announce its departure. It simply drifts, almost politely, a few centimeters farther each year, as though stepping away from a conversation it has been part of for billions of years. And yet, even though the drift is small, the feeling it evokes is vast. For as long as humans have looked upward, the moon has been one of the few truly constant presences in the sky. Long before cities, long before writing, long before agriculture, there was the moon, soft, pale, steady. It lit the paths of ancient travelers. It reflected in the eyes of early hominins who may not have understood the sky, but felt its pull all the same. It shaped the rhythms of hunting, gathering, and movement. It gave a sense of time before clocks existed. It is no wonder that so many cultures saw the moon as a companion, a guardian, a watcher, a presence that was always there. To learn that this companion is slowly retreating is to feel a quiet ache, a subtle recognition that nothing, not even the sky, is fixed forever. But the feeling goes deeper than nostalgia. It touches something universal about the nature of relationships and the passage of time. Because the moon's departure embodies a truth we experience in our own lives. The most significant changes are often the slowest ones. Friendships shift not in a single conversation, but over years. People drift apart not through dramatic ruptures, but through small differences accumulating quietly. Families evolve, children grow, loved ones fade. And often it is only when we look back that we realize how far things have moved. The moon's retreat mirrors this pattern perfectly. It moves away just a little, too little to notice in a lifetime, too little to feel. And yet, across deep time, the change is undeniable, measurable, permanent. In this way, the moon becomes more than a celestial body. It becomes a metaphor for the way life changes, slow, gentle, but unstoppable. But there is another reason the moon's departure feels personal. We evolved under its influence. Our biology, our stories, our cycles, even our sense of time were shaped by this drifting companion. Humans lived with the lunar month long before they understood what caused it. Women's reproductive cycles aligned loosely with it. Migratory patterns of animals, and therefore hunting rhythms, were governed by moonlight. Farmers learned when to plant and harvest by watching its phases. Monks tracked it in ancient monasteries. Early scientists measured its position to understand the laws of motion. The moon is woven into us, into our physiology, our culture, our history. The idea that it is leaving us is not just a scientific fact, it is a symbolic one. It reminds us that we are part of an unfolding cosmic story, not observers standing outside of it. Every tide that pulls at the shore pulls at us too. Every fraction of a millimeter the moon drifts away is a moment in an ongoing relationship, one that began long before we arrived and will continue long after we're gone. When people first hear that the moon is drifting away, the response is often quietly emotional, even if they don't say it aloud. There is a sense of loss, even though nothing has yet changed in the sky. The moon looks the same tonight as it did 100 years ago. It will look the same tomorrow. But perhaps the emotion arises because the drift forces us to think in scales we rarely consider. Human life is measured in decades. The moon's life with Earth is measured in billions of years. To glimpse that scale is to step outside of ourselves for a moment. It is to feel the fragility not only of human relationships, but of planetary ones. And fragility, paradoxically, can make things feel more precious. The moon's slow escape gives the nights we see now a kind of tenderness. This is the moon at this distance, this exact luminosity, this exact size in the sky, only for a short moment in cosmic time. Once it was much larger, one day it will be smaller. We are living in the middle of a transition within a relationship that spans geological ages. There is beauty in that, a beauty rooted not in permanence, but in passing. This sense of passing is also tied to the moon's symbolic role across cultures. The moon has been the keeper of cycles, waxing and waning, disappearing and returning. Its phases became a metaphor for renewal, loss, and rebirth. And yet, beneath those cycles runs a deeper trend, a one-directional drift outward, subtle enough that no ancient culture noticed it, but real enough that we can measure it today with laser beams. The coexistence of cycles and irreversible change mirrors the way human life feels. Days repeat, weeks repeat, seasons repeat. But the deeper arc, our aging, our evolving relationships, our shifting sense of self, moves only one way. In the moon, we see both repetition and departure, constancy and change. There is also something comforting about the fact that the moon's leaving is not a rejection. It is not the moon breaking from Earth's gravity or abandoning its orbit. It is simply responding to the laws of physics, laws that give Earth longer days, calmer tides, and more stable climates. The retreat is natural, predictable, gentle. It is the kind of departure that holds no malice, only inevitability. In a way, the moon's slow movement away from us is not a tragedy, but a transition. It marks the evolution of a relationship rather than the end of one. Even far away, the moon remains gravitationally bound to Earth. Even at twice its distance, it will still shape tides, still influence climates, still mark time. The bond remains even as the distance grows. For many, this idea resonates deeply with human experience. Relationships stretch, people change, distance grows, but often the bond, the memory, the significance remains. Maybe that is why the moon feels so personal. Maybe that is why its retreat feels familiar. It reflects the quiet truth that change is not the opposite of connection, but part of it. And perhaps the most human feeling of all is recognizing that we are witnessing only a moment within a much larger story. A story that began long before us. A story that will continue long after us. A story written in gravity, silence, motion, and time. The moon's departure asks us to hold two feelings at once: gratitude for what is here now and acceptance of what will eventually change. And as this gentle chapter closes, another question rises, soft and inevitable. What does this story of drifting worlds teach us about the nature of change itself and the quiet ways the universe evolves?